Welcome back. Today, I want to continue telling you about the Python data science stack. And in particular, I thought we could talk about the NumPy package, which is kind of a, as I mentioned on Monday, it's like a the core of many data science libraries in Python, and also just super useful on its own. So let me share my screen so that you can follow along with the slides. Okay. Oops. Okay. So I showed this picture. So I ended with this picture at the end of last class, kind of trying to show, you could think of like Python as the core, and then the way the Python ecosystem is organized is there are these like libraries that are built on kind of Python that use kind of low-level Python and or C functions. And then you've got like a set of libraries that are built on those more basic libraries. And then kind of as you expand outward in this like, expanding ripples diagram, you get to higher and higher level libraries that do more complicated things and that are built on the things below it. And so that's what gives Python a lot of its power, is that you can build new tools using the other tools that you develop. So the pace of kind of discovery and development is like accelerating. Okay. Before we dig into NumPy in more detail, it's also time for us to start thinking about assignment 4, which I still haven't given a specific due date for, because I want to get through some of the basic data science stuff before we do assignment 4. But assignment 4 is going to be the first assignment where you're like actually analyzing a data set, doing all the analyses, and then using the analyses that you do to tell your stories. So you're going to be putting another story together like you did for assignments 1 and 2. But for assignment 4 and for the remaining assignments in this course, you'll kind of be building it up from scratch, or sort of mostly from scratch. The way that kind of my suggested workflow for working on stories is to use these project templates that I put together. Each project, if you can see in the screenshot here, comes with like a notebook of the sort you submitted with assignment 3, and then a README file, which kind of gives you, that's where you put like the documentation and links to data sets and that sort of thing that go with your project. And then if you dig into the notebook, I have like a template or like a demo example notebook set up that includes like a bunch of it imports a bunch of libraries you may find useful for working on your projects. You won't necessarily use all of these libraries in all of your projects, but it's a place that you might want to start, with your new stories that you're putting together. You could, maybe get some mileage out of the demo. You don't have to, but you can. Okay. And then there are more detailed instructions if you like click on the assignment 4 link or go to this project template link. So when you start working with real data, you're going to find probably quickly that real world data sets can be really, really messy. So a major difference from like, compiling figures you find on the internet, like you did with assignment 2 or drawing things by hand, and like working with real data, is things tend not to be well organized when you start out. And so a lot of the challenge in working with real data ends up being like kind of wrangling the data or corralling it into a easier to work with format. One way of storing data and manipulating data is using this NumPy library that I want to dig into. So to give you a little bit of background, NumPy stands for numerical Python. And as I've mentioned a few times, it's really the core of the data science toolkit in Python. So many libraries are built on Python, or on NumPy, or on packages that are in turn built on NumPy, including like the Mars rover and helicopter that they're running NumPy based tools. So much of the internet runs on NumPy, or on tools that are based on Python and NumPy. So very wide range of applications. The core thing that NumPy does is it gives you access to this new type of Python object called an array. It does some other stuff too, but the main thing is it gives you access to an array. And an array is like an n-dimensional table of numbers. So most commonly, n will be either 1 or 2. So a one-dimensional table of numbers is like a row or a column vector, like a stack or a row of numbers. And then a two-dimensional table of numbers would be like a matrix. Sometimes it's useful to represent things in more than 2 dimensions. So like if you've worked with brain data, like if you have 3D volumes of like brain activity from a fMRI experiment, you could represent a brain image as like a 3D matrix, or a 4-dimensional matrix if you have one 3D matrix for each time point. And NumPy supports all of these sorts of formats and can work with data stored in these formats really efficiently. A tensor is like a 3 or higher dimensional matrix. And then a vector is like a 1-dimensional matrix. And a matrix is a table of numbers, usually 2D. Okay. And then in addition to introducing this kind of new data type, one of the reasons that NumPy is so useful is it gives you a lot of like useful functions for working very efficiently and quickly with arrays or matrices. So it's got like linear algebra functions for working with matrices, calculus functions, like all your kind of trig functions that you might have on like a graphing calculator. It's got random number generators, some useful probability stuff, lots and lots of useful things. It's a hugely feature-rich package, and there's decent documentation. I've included a link to the, do you all still have the link to the slides that I posted? Would it be useful to repost the link? Yes, okay. Let me pull it up. Okay, so I'll give you the like compacted version so that it's easier to take notes with. Okay. By the way, please jump in with questions if anything I'm saying doesn't make sense. Like it's not going to be useful if I'm just kind of talking at you and no one's following along. So if you're confused about like, okay, how could I use this? Why is what you're saying important? Can you help contextualize? Let me know.
Can you help contextualize maybe?
Yeah, anything in particular, or the whole endeavor, or
just like when we would be using this in this course?
Yeah, so what I'm suggesting is like, if you have a data sets are often just collections of numbers. And then you have to, so you might have like a spreadsheet or measurements that are streaming in over some device, or like a list of files or something like that, each containing some numbers or text or something. Data sets can come in all sorts of messy formats. And in order to work with those data sets efficiently in Python, you need to change the format that the data sets come in to something that's easy for you to work with. And NumPy arrays are are a really nice way of organizing data. So the trick that you kind of usually want to do is, can you turn your messy data set into like a 1 or 2D table of numbers? So like you have to figure out, okay, what are the rows going to be? What are the columns going to be? How do I fill in the entries? And so part of data wrangling is like reading in your files systematically and filling in your tables and matrices and and all that. Once you get your data set in a convenient format, then you can apply other analysis tools that are, like making plots and running stats and all that sort of thing. Is that?
Yeah, definitely.
Okay, great.
Do you think that using these tools is like within the ability of maybe those of us who haven't coded yet, or do you think this is just something that we should be like familiar with?
Oh yeah, no, I definitely think it's achievable. Yeah, so I want to go through a bunch of examples of like, how do you actually use this package? So NumPy is like the first in a line of useful packages that we'll learn about. But I think it's going to be really helpful if you can actually use NumPy. Plus, I know everyone has different career paths. We haven't talked about careers, but maybe we could do that at some point in this course. But if you are thinking about like a data science trajectory, NumPy like scales well to really big data sets. So if you wanted to work for like Facebook or Google or a big company that generates like tons and tons of data, you really need like kind of fancier tools than just standard Python in order to do that efficiently. Okay, so like what I'd recommend is, if you open up a collaboratory notebook, just like a new session, I can even do this in another tab. And then let's see. So what I recommend is just like start a new notebook and then connect to a new server, and then you can import NumPy as NP and then run that line. So Shift Enter, and then you can kind of type in the commands that I'm showing here and follow along and dig into things, ask questions if what I type in like doesn't work for you, or if you're like, what if I type this instead? The best way to learn this stuff is to like actually use it and see what breaks, see what's confusing, and then kind of build from there. So the way you import NumPy, so NumPy is automatically available when you start Collaboratory. There's nothing you have to install. And the way you get access to it is import NumPy, and I almost always use the as keyword to rename NumPy, which is annoying to type, to NP, which is a numerical Python. That's much easier to type. There's a bad way to if you've taken CS1, I don't know if they're still doing this. Some years they teach this really terrible habit of saying from NumPy import star. Do they still do this? Yeah, it's a really, really bad practice because it changes your Python workspace and it can make it ambiguous which functions are coming from which libraries. So you really shouldn't use the star operator. It's like super insecure to do that. So if you end up working in industry or like you want to work on some big research project, this is like inviting, it's just like asking for trouble to use this star notation. That's why I didn't even mention it when I introduced modules. But this is a safer way to work with the library. Okay. So the one way you can create arrays is to use a list as a template. So square brackets 1, 2, 3 makes a list of the elements 1, 2, 3. And then if you call np.array, that's going to create a new instance of an array object containing the elements 1, 2, and 3. So let's explore that. So if we just print out A, it's going to print out, okay, now it doesn't look like a list anymore. It's like an array object, and the elements in it are 1, 2, and 3. Then we can start to manipulate it. So like one operation that NumPy makes really easy is like, what if I want to add a constant to all of the numbers in this array? Well, you can do that by just like adding, like just with the plus notation. So you couldn't do this with a list. This would just fail. But you can easily do it with an array. So what it's doing is it's actually inside NumPy, this 2 is being copied to for each element of the array, and it's being reshaped to be the same size as this array, and then the corresponding elements are being added. So if I had some other array, B, let's say like 4, 5, 6, I could also say like A plus B. That'll work just fine. So 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. So that's much, much more efficient than working with lists, or it's much easier than working with lists. And you can do any operations. You could say like A times B, that broadcasts just fine. A times 2 broadcasts just fine, etc.
Can you only put, sorry.
Yeah.
Can you only put numbers inside these NumPy arrays, or do they hold other things as well?
Yeah, let's try it. So C equals, yeah, so let's have a list like apple, banana, cat. So now that's just a perfectly fine list. Can we do NumPy array of C? That's totally fine. There are some limitations. Does anyone know this movie? It's an old one. There Can Be Only One. No, it's called Highlander. It's actually a terrible movie. It's got Sean Connery of blessed memory. Yeah, and it's truly bad. It's about this like race of immortals who have to kill each other by cutting off each other's heads with magical swords. Anyways, there's this recurring theme, there can be only one. It's appropriate for NumPy because even though NumPy arrays can contain values of any data type, you can't mix and match them. So it's perfectly valid to have a list comprised. So this is a fine list. You can mix and match data types. So we could say like type, you know, perfectly valid to have like some elements are strings, some elements are ints. That's fine. But if I say np.array of C, then it only allows you to have one data type. And so the way it gets around one being of type int and everything else being of type string is it converts the int to a string here. So you can really only have one data type, even if you create the array with something else. That's a difference with how lists work. And the way you read out the data type is you can say like the array name dot d type. That didn't work. Oh, because C is not an array. C is, yeah, okay. Yeah, C is a list. And then we could say like a dot d type, that's 64-bit integer, etc. We can also look at the shapes of an array using the shape method. There's some nuance here. So if you have a one-dimensional list, so just like a vector, like a sequence of numbers, then NumPy treats a one-dimensional thing as neither a row or a column vector. It's just a vector, and the orientation is just ambiguous. And the way that that's represented is it's like a three-dimensional thing, but with no other dimensions. And it like gets returned as open parenthesis, the number of elements, comma, close parenthesis. It's kind of weird. But you can, let's say I wanted to make a matrix with A and B stacked on top of each other. So let's, we could say, here's the syntax. So I say np dot vertical stack means you're stacking vertically, v stack, and then a list of the things I want to stack. And now AB is going to be a 2D table with A in the first row and B in the second row. And then now the shape of AB, the thing I just made, has 2 rows and 3 columns. So we can remember which one is the rows and which one is the columns. So rows always come first, columns always come second. I remember it like remote control, like R and then C. Anyways, that's a thing. Okay. Oh yeah, this is useful. Size tells you the total number of elements, and that's equal to, so I guess, you know, it ignores the dimension, so it's like collapsing across all dimensions, how many things are in the array. It's equivalent to if you take the product of the shape. Oh man, I don't know why I take that. Yeah. So AB.shape is 2, 3. 2 times 3 is 6. And that's the number of elements. Ooh. And then there are lots of useful ways of like, oh yeah, Nathan. Yeah, just jump in. You don't have to raise your hands. You can just interrupt. Yeah.
I was still like a little confused on like what shape does that just like tell you like the amount that's in the array, comma, like something, or
So it tells you the number of rows, that's the 2 here, and then the number of columns, that's the 3 here.
okay, I see. Thank you.
If I horizontally stacked them, that's valid too. So now A is going to be stacked next to B, and now things work a little differently. Now A is going to be, or AB is going to be a 6-element, 1-dimensional array. It's a little weird. And then if you have like an n-dimensional thing, there's a generic, I think there's a D stack also. Let's see what this does. Yeah. Oh yeah. So D stack, so it's like vertical, height, depth. This makes a 3D array where you have 1 row, 3 columns, and then 2 depths. So now you're like, it's like the same numbers, but now it's like shaped slightly differently. And then in general, you can have like stack, and then if you specify an axis, you can make it equivalent to, whatever, any of these. So if you stack it along the 0th axis, that's like stacking down the rows. You could stack it across the columns. You could stack it depth-wise. Oops. Interesting. Apparently you can't stack it depth-wise. Let's see if you can. Nope, you can't. I guess it can only go up to number of dimensions plus 1 of those arrays. In general, though, if you were starting with things with more than 2 dimensions, you could use stack to call out whatever dimensions you wanted. Okay. Oh yeah, other useful things. So you can reshape. So AB now is something with 3 rows and 2 columns. I could say, I could reshape it to something with 2 rows and 3 columns. And so what it's doing is it's taking the numbers left to right, top to bottom, and filling in the entries of a matrix that has 2 rows and 3 columns. So 1, then 4, that gets the first row, that's these entries. Then 2 is this one. And now the next entry is 5, and then 3 and 6. See how that works? Does that make sense? How y'all doing? Good, okay. And then you can reshape it again. That's totally fine. That'll get you back what you started with. You can even add dimensions. Yeah, so now it's a 3 by 1 by 2 table. or matrix. And then you can add as many dimensions as you want. Yeah, like, you know, this is a little bit weird, but now we have a 1, 2, 3, 4, 5, 6 dimensional tensor with 3 rows, dimensions, well, if we call this dimension 0, dimensions 1 through 4 have length of 1, so you know nothing in them. And then the last dimension, dimension 5, has a length of 2. So it's a 3 by 1 by 1 by 1 by 1 by 2 table. Does that make sense? Okay. Slicing is important. So the way you can get out, there are a few interesting ways of getting out numbers. So AB now is a 3 by 2 table of numbers. You use square brackets to get out specific entries in this matrix. So I could get out the value on the row 1, which is the second row, and the first column. Let me just print it out again so you can see for reference. So it's row 1. So remember, it's 0 index. So this is row 0. This is row 1. And then, so that's this 1 here. And then this is column 0. This is column 1. So that's where this 2 is coming from. And then I could get out the whole second row if I replace the 0 with a colon. Colon means just take the whole thing. I could get the whole first column by saying take all the columns, all the rows, but the first column. Or all the rows, but the second column. Or I could say just rows 1 to the end and the second column, etc. So that syntax is really powerful. So that's called slice notation. There's a bit of weirdness. Oh, actually, before I move on, ravel is also often useful. It changes your weirdly shaped array into a one-dimensional array. So it just takes all the numbers and strings them out into a single vector. So that's often useful if you want to like turn, I don't know, sometimes you might want to turn like a whole image into a single list of numbers of like RGB pixel intensities. And this is just like one line for doing that. And then you can reshape it back to the, whatever shape you want. And because everything is always going from like left to right, top to bottom, reshaping something that you've in turn reshaped is like an invertible operation because you're always taking numbers in the same order. So so NumPy has like hundreds of little tricks you can do with matrices. So like I can't like go through the whole list. So it's like what I'm trying to do is like give you a sense of, okay, what are some of the like kind of methods that I use most, and then also like what's the logic here? So that's kind of the most useful thing is like, okay, so I have this table of numbers. Now I want to manipulate it. I might want to select out different pieces of it. How do I do that? And what sort of logic, like, can you build up intuitions about like what sort of logic were the creators of this toolbox using when they decided to design it in a particular way, or what sorts of things could I expect? Like if I want to get out every other element, like how might I expect to do that? That sort of thing.
I had a quick question about, I'm still like a little confused about like what reshape does. Is it like is it basically like reshaping your arrays to like have like the certain amount of columns and rows?
Yeah, exactly.
Okay, because like for the one where we did AB 2, 3 and like just that, I wasn't quite sure like why like 3 was on the bottom row and like 4 I guess was on the top.
Yeah, so what's happening here is, so here are the numbers. So AB is a 3x2 array. So it has 3 rows, 2 columns. And here is a printout of what that looks like. So the first row is 1 and then 4. The second row is 2 and then 5. The third row is 3 and then 6. The way reshape works is you take an array and that gives you like the values. So the literal value, it's just going to be a list of values. So you can think of it as, here are the values.
Okay.
And then, so one way of picturing what reshape is doing is it's like, you can imagine unraveling the matrix into a single list of numbers. And now I'm going to use that list of numbers to fill in this new matrix that has 2 rows and 3 columns. And I'm just going to do that by starting with the beginning of this set of values and going right to the end. So one thing is that the product of the list of sizes you pass in has to equal the number of elements in your list. Otherwise, you can't reshape it. So like this will throw an error. But what's happening is, okay, so 1, 4, and 2, those are the first 3 values in this array. And so that becomes my first row. And now I've moved from left to right on the very top row. And so now I move to the leftmost entry of the next row down and start with the next elements of the array that I'm reshaping. And so I put 5, 3, and 6 in the next row. And then I've run out of elements and my matrix is all filled in. So now I stop.
Okay. Yeah, that makes sense. Thanks.
Sure. Yes. Repeating and tiling is often useful. Well, might be worth going through a few of these. Let's see. Yeah, so let's see. Oh, what's the syntax here? I'm gonna have to look it up. Oh, is it just, oh, that's weird. Interesting. Okay, that's not what, that's, yeah, okay. So what's happening here is you pass in a, okay, let's get back to AB. So we have our table of numbers, 1, 4, 2, 5, 3, 6. The repeat command is going to replicate the rows or columns the number of times we specify. So the first argument that's useful is axis. So axis equals 0 means we're working down the rows, and then axis equals 1 means we're working across the columns. And then the thing that we're operating on is the first argument here, AB. And then what I pass in is the number of times each, in this case, column is going to be repeated. So I have 2 columns, and so I need a list of 2 things. And the first number is going to be the number of times the first column gets repeated. And the second thing is going to be the number of times the second column gets repeated. So like if I repeat something 0 times, that deletes that column. That could be useful. And then if I repeat something 5 times, that's going to create 5 copies of that column. If I let's see if this works. Yeah, so I can add a, oh, whoops. Sorry, let's see. Now you get to see all the things that can go wrong. Oh goodness. Let's see. What did I do here? Oh, okay. Okay, I just forgot a parenthesis. Okay, so now AB is going to be, it's going to have a third row on it, or sorry, third column. So if I use repeat, this is going to repeat the first column 1 time, the second column 5 times, and the third column 2 times. I could also do this down the rows and say, I'm going to repeat the first row 1 time, the second row 5 times, and the third row 2 times. Does that make sense? And then a related command is tile. So repeat preserves the order. And then a related command is tile. And here, we're making a copy of the full table, but then pasting it next to itself the number of times we specify. So if I wanted the table pasted next to itself once, I could create a tiling, like you could think of it like making a mosaic of the repeating elements of the table. We could like copy the table once down the rows. So we have a 1 here, and then twice across the columns. So now I've created AB next to the table AB. Does that make sense? Could also be useful to visualize this. So we could say like, okay, here's the original thing. But then if I tile it next to itself, it's gonna like copy this image next to itself, or I could tile it, 10 times, copy it next to itself 10 times. Or I could tile it 3 times vertically and twice horizontally. Does that make sense? Cool. Ooh, let's see. Splitting is useful. Let's see. So let's see. H split, I think, just gives you oh yes, you have to specify the number of parts. So we could split the array horizontally into like 3 parts. That'll give you a list of arrays of the columns grouped into 3. I could split vertically into 3 parts. That'll give you a list of the rows grouped into 3 groups. And then you can split like, over any dimension using the axis command. Ooh, right. And then finally, sorting is also useful. Let's see, so ab.ravel is this whole mess. np.sort of ab.ravel will sort all the values from like in ascending order. So that returns a new matrix of the sorted values. And then another kind of useful thing is if you do argsort, instead of giving you the sorted values, it gives you the indices if you want to take this unsorted matrix and then sort the values. Argsort gives you the indices of the values in the thing you pass in that you can use to construct a sorted array. So if you did ab.ravel of argsort, that will give you a sorted array. So this is sometimes useful if you want to like get the index of the lowest, like the first 10 values or something like that, or the first 10 lowest values, then argsort can be useful. A-range and linspace are also useful. So do you remember the range operator for like for loops? So you could say like for I in range 10, print I. What's that going to do? What do we think?
It's just going to print 0 through 9.
Yeah. NumPy has an equivalent thing. Kind of works the same. It's called A-range, but it actually produces an array instead of like a range object. That can sometimes be useful. So if you want to just like get the count of the numbers like 0 through n, and then there's like nice options. So if you wanted to go 1 through start with 1 instead, that's fine. If you want to count in increments of 0.5 instead of 1, you can do that too. if you want to count backwards, that's totally legit. Yeah. And then another related command is linspace, where you go from, so a range, you specify the start point, the stop point, and then the step size. In linspace, you specify the start point, the stop point, and then the number of steps. So it figures out the number of steps for you. So if I wanted like the values from 1 to 10 inclusive and 100 steps, then it'll, you know, create this for you. And then you can also, so this linspace will create linearly spaced values. So like just evenly changing, and then log space will create logarithmically spaced value. Logarithmically spaced values. All right. Yeah. Right, you have to, it's specified using a weird syntax. It's specified using like e to the, like the natural log constant raised to the first value, and it goes to the like e to the last value. So if you want to specify log spaced values ranging from like a particular base 10 number to an ending in another base 10 number, then you have to take the log base 10 of the first number as your starting point, and then log base 10 of the second number as your ending point. So what's happening here is early in the sequence, you take smaller steps, and then later in the sequence, you take bigger steps. So that can be easier to see if you just take a smaller number of steps. Okay. Zeros is also really useful. There you create, you can create an array of zeros. The way you do that is you specify the number of values in each dimension. So if I wanted like a 3x6 array of zeros, then that's how I do it. And then there's also an equivalent function called ones, which does the same thing, but fills in ones instead of zeros. And then another useful thing, so if I have like an existing array and I want to make an array of the same shape that's all zeros, one way of doing that would be like np zeros, and then the shape is ab.shape, or a shortcut is like np.zeros like, and that's like a shortcut for this syntax here. So it'll create an array of zeros that looks like the other thing that you pass in. And I think there's a ones like also. Yeah.